Welcome. We will be looking at 2 by 2 determinants. So we will be defining this 2 by 2 determinant, and we will see how how the 2 by 2 determinant comes about when we try to answer the following question. So let's say we want to find the area of the parallelogram spanned by the vectors a and b in the 2 space. So A has components a1, a2, and B has components b1, b2. So the parallelogram spanned by A and B is either going to look like the one on the left, or it's going to look like the one on the right, which depends on the angle between the two. So if the angle between the two is an acute angle, then the parallelogram is going to look like the one on the left. If the angle between them is an obtuse angle, then it's going to look like the one on the right hand side. So again, the goal is then to find the area of the parallelogram spanned by A and B. Again, what we're looking for is a formula for the area in terms of the components of A and B. So A and B are given, and we want to express the area in terms of their components. Okay, so how do we find the area of a parallelogram? Well, to find the area of a parallelogram, you need to know the height of this object. So to find the height, basically from the tip of A, we make a vertical line onto the vector B, or in the second figure, from the tip of A, you make a vertical line onto the straight line passing through B. In either way, the height is labeled in both figures. So let's recall that this vector this brown vector here, that's the projection. That's the projection of A along B, and in this picture, this vector is the projection of A along B. Recall that the component of A along B in the first figure would be positive, and it will be negative in the other figure. And the relationship between the component and the projection is that the magnitude of the projection vector is equal to the absolute value of the component, which is a scalar. So basically, then we know, this side is the length of A. So in order to find height, then if I know this, if I know the magnitude of the projection vector, or if I know the component of A along B, which is going to give me the length of this side, then from this right triangle I can easily find H. So that's the idea, to find H. So here is the idea. So the area would be the length of B times the height H. Now what is H? Well, if in this right triangle, if I apply the Pythagoras' theorem, then I see that H squared would be the length of the hypotenuse squared. Here the hypotenuse is the length of A, minus this side here. This side here is equal to plus or minus the component of A along B, but since I'm squaring that, it doesn't matter whether it's positive or negative. So what we have then is H squared is the length of A squared minus the component of A along B squared. Again, the component of A along B is plus or minus the magnitude of the projection vector here. Since we are squaring it, we don't have to worry about the sign of the component here. So then then what I'm going to do is write down the formula for the component of A along B, which is A dot B over the length of B. So we have h squared is the length of A squared minus A dot B over length of B squared, and which is equal to the length of A squared minus A dot B squared over the length of B squared. So this we can combine these two into one fraction, so we get h squared is equal to the length of A squared, length of B squared minus A dot B squared over the length of B squared. Okay, so at this point what we do is that we are going to express each quantity here in terms of the components of A and B. So recall that the components of A are A1, A2, and the components of B are B1, B2. So we have that the length of A squared would be A1 squared plus A2 squared. Length of B squared would be B1 squared plus B2 squared. And A dot B would be A1 B1 plus A2 B2 squared. And the denominator is also the length of B squared. Now what we have to do is we have to do some algebra. So algebra magic is going to do the following. So you multiply out in the numerator, and then you simplify whatever you get, and then you complete the square again. And if you do that, the numerator becomes A1b2 minus A2b1 squared. So then the height squared is this ratio. So therefore height would be the square root of the fraction right here. Now the square root of that would be the root of the numerator, but the root of the numerator would be the absolute value of A1b2 minus A2b1, and then the root of the denominator. Now the denominator here is still is exactly the length of B. Now the reason I put absolute value sign is because the quantity A1b2 minus A2b1 could be negative. So in order to make sure that I make it positive, I'm putting the absolute value there. So now let's look at the area. The area would be the length of B times h. Length of B would be the root of B1 squared plus B2 squared, and we plug in what h is right here, and then what we see is that we are getting a very simple formula for the area, which is the absolute value of A1 B2 minus A2 B1. So the area of the parallelogram spanned by two vectors A and B in the 2 space is simply given by this quantity. So what do we define? How do we define the 2 by 2 determinants? If I have a vector A and B where the components of A are given by A1, A2, and the components of B are given by B1, B2, then the 2 by 2 determinant A1, A2, B1, B2 is given by the following quantity. It is A1 times B2 minus A2 times B1. So this is the 2 by 2 determinant. And so the 2 by 2 determinant then tells us, so the 2 by 2 determinant here, the way we're defining here, is exactly what I have in the absolute value sign for the area of the parallelogram. So basically then, if I have two vectors A and B, where the components of A and B are given by A1, A2, and B1, B2, then the area of the parallelogram spanned by A and B would be equal to the determinant of the 2 by 2 matrix, where the first row is A and the second row is B, but it is the area of the parallelogram up to -1, because remember, for the area we need to take the absolute value of this quantity, and the determinant is this quantity without the absolute value. So the determinant tells us the area of this parallelogram up to -1. Okay, so I am going to stop this video here. In the next video, we will be defining the cross product in dimension 3.